Hi, welcome to Hashtag Math. We will add another piece of information towards the graph of a rational function, slanted asymptotes or oblique asymptotes. They are also going to give us information about the end behavior of rational functions. First, let's understand this type of asymptotes on the graph. Slanted asymptotes are lines, like the one shown, that the graph of the function approaches. As with any other asymptote, the graph of the function must approach a slanted asymptote. And this is what happens. As x approaches positive infinity, the graph of the function must approach the asymptote, either from this side or this side. In the same way, as x approaches negative infinity, the graph of the function must approach the slanted line, either in this side or this side. This is the graph of a typical rational function with a slanted asymptote. How do we find slanted asymptotes from the equation of the function? We again compare the degrees of the denominator and the numerator. Slanted asymptotes occur when the degree of the numerator is by 1 bigger than the degree of the denominator. That is, when the degree of the numerator, which is n, is by 1 bigger than the degree of the denominator, m. Like, for example, f of x. The degree of the numerator, 2, is by 1 bigger than the degree of the denominator, 1. And you see the slanted asymptote over there. But how do we find them? We just perform long division. So let's refresh a little bit long division. If you want to use synthetic division, it's fine also. When we perform long division, the polynomials have to be written in descending order with no gaps. This is what I mean. X squared plus 1 is missing the power of 1. So it is in descending order, but a polynomial has to have a power of 0, then a power of 1, then a power of 2, then a power of 3, and so on and so forth. If one of those powers does not appear, then we have to complete it with zeros. In the case of x squared plus 1, the first power does not appear, and we have to write x squared plus 1 as x squared plus 0x. So we insert a 0 in the places where we have a gap. So we get x squared plus 0x plus 1. And we want to divide 3x cubed minus 2x squared plus x, and then the 0th power is missing, so we have to write a 0. We want to divide that by x squared plus 0x plus 1. Let's recall how you do that. We divide the first term of the dividend, 3x cubed, by the first term of the divisor, x squared, and we get 3x. That is the first term of the quotient. Then you multiply 3x to the entire divisor. That's 3x times x squared plus 0x plus 1, which is 3x cubed plus 0x squared plus 3x. And then go and subtract it here. For that, I'm going to change signs. So 3x cubed, we're going to subtract it. So this is negative 3x cubed. 0x squared, we do negative 0x squared. Positive 3x, we do negative 3x. And then we add, of course, the first cancel. Negative 2 minus 0 is negative 2x squared. 1 minus 3 is negative 2x. And we lower down the 0 and do the exact same thing. Divide the first term here with the first term here, negative 2x squared, divided by x squared, and we get negative 2, which goes to the quotient. Then multiply negative 2 to the divisor, x squared plus 0x plus 1, we get negative 2x squared minus 0x minus 2, and you change signs. We do 2x squared, negative 0x plus 0x, negative 2, and go plus 2. This cancelled out, of course, and we get negative 2x plus 2. The division is ended when the degree of the residue here is smaller than the degree of the divisor. Then by the algorithm of division, 3x cubed minus 2x squared plus x plus 0 divided by x squared plus 1 equals the quotient, 3x minus 2, plus the residue, negative 2x plus 2, divided by the divisor, x squared plus 1. We're looking at end behavior, so we're looking at big values of x. Notice that this term here has the degree of the denominator, and that's always going to happen because it's a division, bigger than the degree of the numerator. So for big values of x, this approaches 0. Thus, the oblique asymptote is y equals 3x minus 2. And we can just graph that line, whose y-intercept is negative 2 and has a slope of 3. So we do 1, 2, 3 up, 1 to the right, 1, 2, 3 up, 1 to the right, 1, 2, 3 down, 1 to the left. This is how the horizontal asymptote looks like. Ooh, doesn't look very straight. And then the graph, as x approaches positive infinity, has to approach the asymptote, either from this side or the other side, and to negative infinity, again, it has to approach the slanted asymptote. And this is how the graph of this function looks like. You see, as x approaches positive infinity, the graph is approaching the asymptote like that towards positive infinity, and as x approaches negative infinity, the graph is approaching the asymptote towards negative infinity. And thus, it's describing the end behavior. As with horizontal asymptotes, the graph of a function may cross a slanted asymptote, but only towards the center. So you do not ever touch a vertical asymptote, but you can cross slanted or horizontal asymptotes towards the center of the graph and never towards the ends. Let's look at one more example. The degree of the numerator is 4 by 1 bigger than 3, so it has a slanted asymptote. Let's divide the polynomials. So we're going to divide 5x to the 4th power plus 0x cubed, because the 3 doesn't appear, minus x squared plus 0x, because x to the 1st power doesn't appear, plus 3, divided by x cubed, complete here for x squared, complete here for x, then minus 1. And again, when we divide the first term by the first term, we get what? 5x. Then multiply 5x to x cubed plus 0x squared plus 0x minus 1 to get 5x to the 4th power plus 0x cubed plus 0x squared minus 5x, and subtract. Change signs. Negative 5x to the 4th power minus 0x cubed minus 0x squared plus 5x. These cancel out. This is 0. This is negative x squared plus 5x plus 3. And it's done because the degree of the residue is smaller than the degree of the divisor. And our slanted asymptote is right here. Y equals 5x, as you can see in the graph. And you see the graph approaching the slanted asymptote like that. In this example, we can see the function on the graph. We notice that we can factor the denominators, so let's do it. H of x equals x plus 3 squared times x minus 1 over x plus 3 times x minus 3. And the factor x plus 3 from the denominator cancels out with that 2, leaving us x plus 3 times x minus 1 over x minus 3. The value x equals negative 3 is what? A whole, or a removable discontinuity. And do we have oblique asymptotes? You're looking at the graph. Yes, we have them, because the degree of the top is 2, which is by 1 bigger than the degree of the denominator, which is 1. So we FOIL this, x squared plus 2x minus 3 divided by x minus 3, and perform long division. We're going to divide x squared plus 2x minus 3 by x minus 3. No gaps, so we're fine. Divide the first by the first, we get x. Multiply x times x minus 3, get x squared minus 3x. Change signs. Negative x squared minus 3x, and add negative x, lower the negative 3, and do the same procedure again. Divide the first term by the first term. Negative x divided by x is what? Negative 1. Multiply negative 1 to x minus 3, we get negative x plus 3, and change signs. X minus 3, negative 6. Where is our slanted asymptote? Right there. Slanted asymptote is y equals x minus 1. As you can see in the graph is approaching the asymptote here and here.